We're going to do an activity today called the Current Balance Lab. The purpose of this activity is going to be to find the magnetic field strength that's caused by a big magnet, basically. The magnet looks like this. It's actually a series of small U-shaped or horseshoe magnets that are put together to basically form one big magnet with a north pole and a south pole, as you can see right here. We want to find the magnetic field strength that's caused by this magnet. We're going to do that in two different ways. Part one, going to look like this. The setup is going to look like this. It's at the back of the room right now, but you can probably see it up here a little bit better because it's a little bit bigger. We've got a power supply that's got a couple of wires hooked up to it, a black wire and a red wire hooked up to it. The black wire and the red wire go to this arm, we call it, this arm right here, and they apply an electric current through part of this arm, through a little wire in this printed circuit board, and back through the other arm, back to the power supply. So we get an electric current that goes through this printed circuit board that is in between, or is in the gap of this magnet. So now we've got a wire with an electric current moving charges in between two magnets. We've got a wire with an electric current in an external magnetic field. That's going to cause a force. It's going to cause a force on the wire, but it's also going to cause a force on the magnet. If the wire pushes up on, if the magnet pushes up on the wire, then the wire is going to push down on the magnets. There's an equal and opposite force there. In the first experiment, you're going to keep the length of the wire constant. You're going to change the value of the current that goes through this wire, and you're going to keep the length of the wire constant. Here's how it goes. Here's how the activity actually goes. You're going to put the wire, which is this printed circuit board, literally in between the poles of this magnet. And you're going to press 0 on this scale if it's not reading 0 already. So turn the scale on if it's not turned on, put the mass on, the magnets on, and then press 0 or tare if it's not zeroed already. You're going to turn the voltage knob of the power supply to the far right. The current knob of the power supply, that's the lower one, and they're labeled in case you forget. You're going to turn it to the far left. Right now, the current should read 0. That's the way we're going to start off. Now we're going to adjust the current knob of the power supply. That's the lower one. Turn it up a little bit so that the current doesn't read 0 anymore. Okay, let's say we get a current of 0.2 amps. Record the value of the mass that the scale reads as a result of that. The scale is going to read a mass of something other than 0. It was reading 0 when the current was turned off. Now it's reading something other than 0 because when there's a current going through that wire experiences a magnetic force, but the wire also causes a magnetic force down on the magnets. The magnets are pushed downward. That tricks the scale into thinking the mass is heavier. Therefore, the scale is going to read something other than 0 now. So write down that value. Say 0.2 amps, 0.29 grams. Turn the value of the current again, get another current, get another mass. Get another current, get another mass. And so on and so on and so on until you've got 10 different currents and 10 different corresponding masses. Make sure as you do that you record the length of the wire. Remember, you're only using one length here. You're not changing that throughout this experiment. So write down its value. The one that you're probably going to be using is the one that's 8.4 centimeters long, although before you start your experiment, make sure you check that. Make sure you're using that one. Let's go to part 2 now. Part 1, remember, change the value of the current, keep the same length of wire. Part 2, going to be set up exactly the same way, but in part 2, you're going to keep the current constant and you're going to change the length of the wire. So this little thing in here, this little printed circuit board, you're going to swap that in and out. Okay, you're going to take the 8.4 centimeters out, you're going to put a different length in there. You're going to take that one out, you're going to put a different length in there. This is what the different lengths look like. Okay, literally, take one out, put the next one in. Take it out, put the next one in, and so on and so on and so on. There's only 6 of them. So in the first one, you've got 10 trials, 10 different currents, one length of wire. In the second one, you've got one current, not changing the current now. The length of wire is going to be changed 6 times. 6 trials. Your data table should look something like this. 6 different wire lengths, 6 different masses, and one current. whatever current you choose to keep constant throughout the entire experiment there. Once you've got your data for both trials or both experiments, you're going to do your analysis. The analysis for experiment 1 is going to involve the same two columns that you've already recorded, current and mass, but also an additional column called magnetic force. We're going to find the value of the magnetic force, first of all, by converting the mass in grams to kilograms, and then converting kilograms to newtons by multiplying by 9.81. How can we multiply by 9.81 to get a magnetic force? Doesn't that give us a gravity force? Yes, it does. But remember, the scale was tricked into thinking the mass was heavier. So really, it's interpreting the magnetic force that's pushing down on those set of magnets as a gravitational force. So if we multiply that extra mass that the scale reads by 9.81, we will get the gravitational force that the scale thinks it's reading, which actually corresponds to the magnetic force that it's truly reading. Do the same thing for experiment number 2. Take your mass, multiply it by 9.81, get your magnetic force for trial number 2. Now you're going to plot two graphs. The first graph is going to be a force versus current graph. Remember, in the first experiment, you kept the length of the wire constant. You didn't change it, but you did change the length of, the current. And of course, responding to that was the magnetic force. When you do that, you should get a graph that's a straight line. This experiment almost always works out very, very well so that we get really, really good data. It should work out to be a straight line for you. When we see that straight line, we're going to write down the equation that applies to every straight line. Y is equal to mx plus b. Then we're going to replace y with whatever appears on my y-axis, force. Replace m with the word slope, just because I don't want to get m mixed up with the slope mixed up with the mass. I'm going to replace x with whatever appears on the x-axis, which is electric current. Okay, the symbol for electric current is a capital I. Now, B stands for the y-intercept. We're just going to scratch that out because there is no y-intercept in this one. Now what I want to do, and pay really close attention to this one, okay? Now what I want to do is take an equation from my data sheet that is relevant here. The equation from your data sheet is actually one that you haven't seen before. I'll briefly explain it now, and we'll talk about it in more detail the first of the week. F is equal to ILB. That stands for the force that acts on a wire, the magnetic force that acts on a wire as it's exposed to an external magnetic field. F stands for the magnetic force. I stands for the current. L stands for the length of the wire. B stands for the magnetic field strength. Let's take the equation that I got from my graph. F is equal to the slope times I. Let's take the equation that I got from my data sheet, and then let's cross off what the two equations have in common. F appears in both. I appears in both. What am I left with? I'm left with the slope in the first one. I'm left with LB in the second one. So we know that the slope of this graph is equal to the length of the wire times the magnetic field strength. The slope we can calculate pretty easily. We've done that since grade 9. The length of the wire we kept constant throughout this entire experiment. It was 8.4 centimeters, right? So put in that value. Solve for the magnetic field strength. Remember, that's the whole purpose of this activity, is to find the magnetic field strength of those horseshoe magnets. In the second experiment, you're going to do something similar, but this time the graph isn't going to be force versus current because you didn't change the current here. You kept it constant. You changed the length of the wire in the second experiment. When you plot force versus wire length, you should also get a straight line. That's also going to be represented by y equals mx plus b. Let's replace y with F, force, m with slope, because that's what m means, x with whatever appears on the x-axis. That's going to be the length of the wire. There is no y-intercept, so again, we can get rid of that. The equation on my data sheet that matches up with that is the same equation as matched up with the last one. F is equal to ILB. Cross off what appears in both. Cross off what the two equations have in common. F appears in both. L appears in both. We're left with the slope is equal to I times B. So in the last activity, the last experiment, we found that the slope was equal to L times B. In this graph, we find that the slope is equal to I, the current, times B. We've got the slope. The current, we kept the same through this entire trial, and you would have recorded it. So once again, we're able to find the magnetic field strength. You're going to calculate, using this graph, the magnetic field strength of these magnets twice. You should get the same value both times. Okay, we probably will get numbers that are slightly off, but you know that if you get the same number, you've probably, or pretty darn close to the same number, you've probably done this correctly. If you get numbers that are way off, then you've probably made a mistake somewhere. What do you got to hand in for this? Well, good news is there's not a whole lot you have to hand in. I want you to hand in your data, and I want you to hand in your analysis. Your data is this table. It's this table. Then your analysis are these two tables along with your graphs and this analysis here of figuring out what the slope represents and then your calculation of whatever the magnetic field strength is. Yep. Does that make sense? Okay, let's get into groups of either 3 or 4. Whatever group that has 3 or 4 and is ready first can start.